Okay, so I'm going to be talking about a body of material that covers how you can apply techniques taken from fairly elementary combinatorial topology to distributed computing. Now, I think this is interesting for a number of reasons. One is that it gives you a fairly simple way of getting very general results that apply to many different models of a computation. The other is that there are some problems for which these techniques provide the only known solution. So it gives you both new results and the ability to simplify and unify existing results. Now that said, I think this material that I've covered here is probably more widely admired than understood, in the sense that it requires, the mathematics behind it is very simple, but it's not mathematics that's familiar to many computer scientists. So people in our community know all there is to know about graph theory and probability, but as soon as you start talking about simplicial complexes, even at the undergraduate level, then everyone starts heading for the door. So the goal of this course is to take all of the material that's out there in conference form, in kind of cryptic journal submissions, explain it in an elementary way, using only the most basic combinatorial mathematics, and to be able to make this comprehensible to people who are computer scientists rather than people who come from mathematics departments. As a side effect of this, we'll discover some, I think, new and interesting mathematics. Historically, whenever you apply an existing branch of mathematics to a new field, it doesn't exactly fit. So you have to take a crowbar and make it, bend it and twist it. And when you do this, you discover some interesting things. So what I'm going to talk about in the first part of the lecture is what is distributed computing. Now, many of you probably know a lot of this stuff, and I hope I don't bore you, but I'm going to emphasize the diversity of models and give you a sense of the different kinds of problems we have to look at. After this part of the lecture, we'll have a short break, and then I'll talk about sort of the fundamentals of applying combinatorial topology to describe distributed computing. So we won't do any technical results in this lecture. This is going to be all definitions and explanations of why things are interesting and what the mathematical concepts are before we get into any non-trivial applications. So in the beginning, as you all know, a computer was just a Turing machine. Our friends who do complexity theory still think this is true. And every time they say, well, why are you working on this distributed stuff anyway? You know, it's not really important. I say, well, whatever your shortest path, latest bipartite graph algorithm is, today you're trying to do it in polynomial time, but next week you're going to be doing it on a concurrent multiprocessor. And good luck with that. So the story is that today we're concerned about what happens when you take a collection of computers and have them coordinate to do useful things. And it's the coordination part that is typically difficult. That's the part that presents the real challenge. And so I'm going to start out with a very simple puzzle. So imagine that we have a collection of processors, and each one starts out with a private value that it alone knows. You know, this could represent a message it got, it could represent a keystroke, it could represent a radar image of something approaching. It's just something that it alone knows about. Now then they communicate with each other, and for now we'll be vague about how exactly they communicate. You know, could be messages, could be shared memory, could be carrier pigeons, we don't particularly care. And at the end we want them to agree on somebody's input. And we want them to do this in a finite amount of time. We want to guarantee that they agree and that the value chosen is somebody's input. And this is called the consensus problem. And it's classic problem in distributed computing. And this is one of the first problems that we'll look at. So if you explain this to people who aren't used to concurrent computing, they'll say, well, isn't this kind of a trivial problem? You know, I always suspected that you guys are wasting your time, but isn't this really confirmation that you're trying to do easy things? And the answer is, well, no, actually, because in many models of computation, a process can go to sleep. And so it might not respond to your answers, and you have to decide, well, what am I going to do if I don't hear from this process? Even worse, the process could crash. So the process might just drop dead. And in that case, it's never going to answer your query. It's never going to give you any more information. And what do you do then? And of course, when you try to devise protocols for this model, you have to worry that the other processes might think that process is sleeping when it's actually dead. Or worse, it might be sleeping and the others are going to assume it's dead. And then it's going to wake up and say, hey, what happened while I was out? So it's the uncertainty about failures that makes these kinds of problems difficult. Now, in order to distill the notion of computation into a fairly simple and manageable form, we're going to focus on a restricted set of problems that we'll call tasks. So a task has the property that we start out with a possible set of input values, and after a finite computation, that is, you can't sit there and wait forever for something to happen, because that requires an infinite number of steps. After a guaranteed finite number of steps, everybody has to choose an output from a set of acceptable outputs. So we just have a collection of possible inputs, we have a finite computation in the middle, and we have a collection of possible outputs at the end. So this is a very simple form of computation. And what we're going to look at is under what circumstances can we solve these problems, and under what circumstances can we not solve these kinds of problems. So suppose we decide that consensus is too hard. So we're willing to lower our standards a little bit and say that instead of requiring that everybody agree on a single value, we'll require that everyone agrees on fewer than k values for some small value of k. So we'll say we'd rather that everybody agrees, but it's okay if the number of distinct values chosen is actually 2 instead of 1. So this is something called k-set agreement. So this is a weakening of the consensus problem. So consensus is one set agreement. So this is another problem that we'll examine as the course proceeds. Another problem is, imagine that we decide to privatize air traffic control over the Atlantic. So right now, if you fly across the Atlantic, I think the planes flying east fly at even-numbered altitudes, expressed in terms of thousands of feet, and the planes flying west go at odd-numbered altitudes. Or maybe it's vice versa. It's a good thing I'm not a pilot. And right now, this is done in a centralized way. You know, there's somebody tells each plane where to fly, and they check and make sure that you don't have too many flying at the same level. But suppose that we decide that it's too expensive to have control towers, and we're going to have each of the planes negotiate among themselves for which altitude they're going to fly in. And here, for example, we have 3 different airplanes, and we have the same problem that an airplane, the radio might fail, they might decide to land and have lunch. All kinds of things can happen. And so you're not entirely sure whether somebody is flying or whether they decided to stop and refuel. And so the question here is, how many slots do we need in order to guarantee, for example, that these 3 airplanes, in the presence of uncertainty, can take unique altitudes? So this is called the renaming problem. And this is yet another problem that we'll look at. So there are many models of computation. One model has to do with what kinds of communication do processes use. So it turns out it matters whether you send messages, use shared memory, whether you have strong synchronization primitives or weak synchronization primitives. So this is one aspect of the model that will change. We'll look at different models of communication. Another question is failures. When can processes fail? How many of them can fail? What combinations of processes can fail? That's also something else that has an enormous effect on when things are solvable and when they're not solvable. And then finally, timing models are also very important. Do processes run at exactly the same speed? Do processes have no bounds on their relative speeds, or do they run at approximately the same speed? Again, these things will have a big effect on the kinds of results we can choose. So let's look at some of these possibilities. So communication, historically the oldest is message passing. That is, each process writes out a message and sends it to another one. This is the basis for modern networks. They might also have read-write memory. So the processes might, say, have a big shared array, and you can write your entry and read someone else's entry. This might correspond to a primitive multiprocessor. Another model is what we call black box memory. Suppose I give you a big read-write memory, and I also give you the ability to do things like test and set or compare and swap and other kinds of powerful synchronization primitives, things that are more powerful than read-write memory. Each of these models is important and interesting in and of itself, and each one will affect how the kinds of results that we can achieve. So message passing here looks like this. Read-write memory looks like that. It turns out that there are a lot of different read-write models. So a very simple one is I can read or write an individual variable in memory. This is, if you write an assembly language program, this is the model that you use. Or you could say, well, I can write memory, but I can take an atomic snapshot of all of memory at once. So I can write something, and then I can instantaneously read everyone else's values. Or you can make it even seemingly stronger claim, which says that I can take a group of processes and have them all write together to different locations, and then they can all take snapshots together. And it turns out that each of these models is exactly equivalent in the sense that you can implement each one out of the others. So in the course, we will use whichever one, we will use sort of the weakest one that is convenient. So whenever possible, we'll just talk about reading and writing individual locations because that's the most natural model. But every now and then, it will be very convenient to switch to one of these more elaborate models because of mathematical convenience. But in terms of computational power, these are all the same. We're not going to go over those results. Those are well-known results in distributed computing. So you just have to believe me on this. Sometimes it's convenient to switch from just simply sharing a memory to a round-by-round model, where the processes work on one copy of the memory in round one, remember their state, and move to a clean copy on each round. And these are typically equal in power to models in which everyone shares the same memory, but again, it's often more convenient to deal with this. Now, I don't expect you to remember all of these details. What I'm trying to impress on you is that in its natural state, distributed computing is very complicated and confusing, and our job here is to make it simple. And so before I can convince you that it's worthwhile to make it simple, I have to convince you that it's complicated. Black box memory is really what you get when you buy a laptop from Dell. So if you look at the spec for any modern multiprocessor, they have instructions like compare and swap, test and set, fetch and add, swap, things that will reach into memory and atomically make a change to the memory, which is more powerful than something where you read, modify, and write it back, because the entire computation is done as a single atomic step guaranteed by hardware. And so it turns out that these will have an effect on which problems can be solved and how quickly they can be solved. Okay, next let's talk about failures. What kinds of failures we can tolerate. So all the failures that we look at here are crash failures. That is, processes halt. If we have time at the end, I'll talk a little bit about how all of this applies to Byzantine failures. That's kind of an ongoing research topic. But for right now, we just assume that a process crashes by falling silent. So it doesn't send you anything evil. It just gets all passive-aggressive and won't say anything. One question is, how many processes can fail? Which processes can fail? For example, in what's called the wait-free model, all but one process can crash. We're not really interested in computations where everybody crashes because it's hard to do anything useful there. But suppose we don't, we want to tolerate failures by any number as long as there's still somebody left to do work. We might say, well, wait free is awfully expensive. Maybe we want to say, well, we really only expect a small number to crash during the time period that we're looking at. So Google, has 500,000 servers, and at any point they expect maybe 2 or 3% to be down. They don't expect 99% of them to crash at once. So T resilience says that at most T may crash. In this picture, a T is 1. Now, in the real world, crashes aren't quite as independent as that. So if you have two servers that are running on the same hardware platform, or two servers that are running behind the same network gateway, then their failures aren't independent, they're highly correlated. So we might want a model where we can say, well, we want to be able to talk about patterns of crashes, where the top two live on the same server and they always crash together. The bottom one lives on a different server. And we don't expect both servers to crash at the same time, but we do expect these failure patterns to happen and not others. So in order to be useful, we'd like to be able to talk about those patterns as well. So the way to deal with this is we're going to use the notion of an adversary. So you think of an adversary as someone who knows your algorithm and is trying to make it either fail or run for a long time. And it controls who can crash and who doesn't crash, subject to restrictions. So an adversary determines which sets of processes can halt. And you can think of this as saying, well, if I design my algorithm, what's the worst case scenario? So you can think of this as a kind of a game between you and the adversary. This is just a convenient way to think about things, but we need to be able to discuss arbitrary adversaries if we want to really be useful. Timing models. So this is something where either the processes can share a clock. We call that the synchronous model. That's historically the oldest model. Because there were processes don't share a clock. And we call that the asynchronous model. And the truth usually lies somewhere between, where processes have approximately synchronized clocks, which can kind of go wrong a little bit. And we'll call that the semi-synchronous model. And what we would like is to find principles that kind of unify all of these. Historically, there's a bunch of papers on one model, then that's no longer fashionable, and people write papers on another model, and so on. But we would like to have kind of a single way of thinking about all of these things together. So in the synchronous model, all the processes take steps at the same time. This is historically the oldest model because before there were any concurrent processors, people thought, well, what are they like? Well, they probably all run on the same clock. Then this model fell into disfavor because when people actually built multiprocessors in distributed systems, it didn't exactly look like this. And now it's coming back into favor because people are building things like graphics chips, which actually are synchronous models. There's a whole PRAM literature that's based on the assumption that concurrent machines look kind of like that. Think about synchronous models is it's relatively easy to detect failures. If I'm expecting a message from you at 1 o'clock and it doesn't show up, then I can assume the worst because I know that either you crashed or you sent me that message. So that means failure detection is easy, although there may be some uncertainty about exactly which round the failure happened in. Asynchronous model, we say, well, in fact, it's too hard, even on a modern processor chip, it's very difficult to deliver the clock pulse at the same time to all the pieces of the chip. So we can say, well, forget about time. We're not going to make any assumptions about the relative speed of processors. One can run really fast and one can run really slow. We can have a processor run really fast, then takes a page fault, doesn't take any steps for millions of cycles, and then it comes back and runs really fast again. So we have a justification for saying that the speeds are, there's no bound on relative speeds, and the speeds can vary enormously over a period of time. Now, the thing about asynchronous failures is failure detection is typically impossible. You can't tell whether an unresponsive process is dead or whether it just went on vacation for a month. In the middle, there's a semi-synchronous model, which there's many kind of variations of this, but the basic idea is that there's a bound on the ratio of the speeds. So I know that if blue takes 2 steps, then red has either taken 1 or 2 steps. And failure detection in this model is possible, but it's slow because you have to time out. And timeouts are typically fairly long compared to a process step times. So in one case, failure detection is easy. One case, it's impossible. In one case, it's possible but expensive. So here is sort of what I've talked about. So we have a number of timing models. We have a number of failure models. And we have a number of communication models. And there's 2 points that I want to make about this. One is that if you take the cross product of all of these things, plus a number of other choices that I haven't told you about, you get an enormous collection of models. This, if you were cynical, you would say, well, everybody needs to publish papers. So if you find some new cross product in here, you can publish papers in there until people get tired of it. But another explanation is that actually many, not all, but many of these combinations make sense in the real world. So there's a reason that we study them. And what we would really like from a theoretical point of view, again, is not ad hoc results having to do with each of these things. We would like kind of a general theory that says, here is a result that holds for every model. Here is where you plug in the model-specific reasoning in order to get the kind of results that you want. And sort of the goal of this course is to give you kind of a general way of talking about all of these things and isolating very small pieces that are model dependent and identifying instead the general principles that cover all of these different kinds of distributed systems. So for example, very common form of distributed system, even though it's often not called distributed, is a multi-core. So this is a sun Niagara. And so a multi-core is basically asynchronous. There's this technicality that I think on Niagara they can do it, but not on a multi-chip Niagara, that is hard. You can't deliver clock pulses simultaneously to the chip because it's too big. But more important at the software level, anytime you take a cache miss, you're delayed for tens of cycles. Anytime you take a page miss, you're delayed for hundreds of thousands of cycles. And if the operating system decides to deschedule you and run someone else, then it could be millions and tens of millions of cycles. So I could have a critical section that takes 100 instructions, and it could take me 1,000,000 cycles to finish it. And this is unpredictable in general. And so in some sense, even though processors do not stop and catch fire, if you are swapped out for a few billion cycles, then we can treat this as a failure without feeling embarrassed about it. So this is a case where we have asynchronous wait-free shared memory. And this is a kind of application that people care about. So this is kind of motivation for studying that model. Distributed computing. Everything from the whole internet to your sensor networks is asynchronous message passing. That is, the processors don't share memory. They send messages to each other. In a sensor network, you can't really afford to put a clock on every chip, and you couldn't keep them synchronized anyway. And in the internet, you don't trust anybody anyway, so you can't really have a very strong sense of time. Although you could argue that the internet might be semi-synchronous in some contexts. Parallel computing, GPUs are basically enormous SIMD machines. All of the processors are executing the same program in the same step, and they have multiple data streams. And this is something where GPUs are a hot area in systems right now because people have discovered that they're good for things other than graphics. So the fact that people are willing to pay lots of money to play games means that the companies that build these things could put a lot of resources into it. And after they did that, people said, well, hey, we can do all kinds of linear algebra, scientific applications, whatnot, on these specialized boxes. But they really are synchronous. They really go in lockstep. Failure isn't really an issue now, but it will be later on when they become much, much bigger. You know, when you have 1,000 processors, you're not worried about one failing, but if you had 100,000 processors, then you had better start worrying about that. Okay, now a little bit of philosophy here. So the traditional way of reasoning about a lot of these things is what I call operational reasoning. That is, you think about processes unfolding in time. You say, well, my algorithm works like this. First you do this, and first you do that, and then you do something else. And then what if somebody else takes a step in between here and there? Well, here's what happens in that case. But what if they take a step here instead of there? Then, well, in that case, you do this. And the problem is that in distributed concurrent systems, the number of interleavings is so huge that it's very difficult to reason about these things if you're thinking in terms of processes that unfold in time. Now, what I'm going to propose here is something that uses combinatorial reasoning, where in some sense we're going to represent all of the possible interleavings and all the possible failures as static mathematical objects. In this case, you can think of them as kind of, there'll be shapes in higher dimensional space. And doing that has a number of advantages. One is people are much better at reasoning about static things than they are about reasoning about dynamic things. Another is that we can tap into centuries of work on different kinds of topology that the mathematicians were thoughtful enough to do for us. So I'm going to rely on a half a dozen classical theorems in combinatorial topology, things like Sperner's lemma, Nerve theorem, simplicial approximation. And we're not going to prove them, because if you want to prove them, that's a different course and it would take a long time. But the statements of these theorems are very simple. And it's easy to understand the statement, even if the proof might be a little bit of heavy lifting. And if you're willing to believe this, then we can make a lot of progress because the ratio of simplicity of the statement of the theorem to the amount of work you have to do to prove it is very high. And this is the equivalent of saying we're going to use an operating system that virtualizes lots of ugly, complicated stuff and gives you a nice, clean interface. So we're going to do the theoretical equivalent of that. So this is the ideological message that I want to send with all of this. So we're going to look at model-independent properties, again, with the idea that we want to take the kind of messy, specific model-dependent stuff and put it in a very small box and be able to plug that into more powerful and general statements. Okay, so I think it's probably too early to take a break, so I'll move on to the second thing. Then let me know when it's time to take a break. Okay, so the first part was, very high level bit of motivation. Now what I'm going to try to do is to tell you a little bit about the language that we're going to use to describe distributed computing. So this is all definitions and models and pictures. And next time I'll start doing some actual results. But this time I want to make you comfortable with a particular way of thinking about computation, which for some of you at least may be unfamiliar. So I'm going to talk about basic concepts of combinatorial topology. And by basic, I mean really basic. So I'm going to, every time I need a non-trivial construct, I'm going to introduce it right before we use it. So I'm just going to give you the basic language here, and then when we start using Sperner's lemma and so on, I'll tell you about it immediately before you use it. I'm not going to front load the mathematics here, because I want people to feel comfortable with the vocabulary. And in particular, I want to focus how you take these ideas and model distributed and concurrent computation. That's the one bit that I want to convey in this lecture. And in its heart, it's very simple, but it may be unfamiliar. And so I really want to emphasize this particular structure. And in particular, one of the themes that we're going to come back to a lot is the duality between combinatorial and continuous mechanisms. So a computer program is a completely combinatorial, discrete thing. You know, it doesn't exist in space. It's all zeros and ones. It's not continuous. But what we're going to do is we're going to move back and forth between discrete and continuous mathematics opportunistically, because it turns out that there are a lot of theorems that would either be very cumbersome to prove in the kind of discrete combinatorial style that we use a lot in computer science, or we simply don't know how to do it. And since typically the continuous arguments are very simple, there's no real incentive to try to figure out how to do that. So start with something basic. So a vertex, in a purely combinatorial sense, is just an uninterpreted element of a set. Later on, we'll add a little bit more baggage, but you can think of it that way. From a geometric point, you can think of a vertex just as a point in a high-dimensional Euclidean space. So we're going to move back and forth between thinking of a vertex as just an abstract object and something that lives in actual space. So a simplex, combinatorially, is just a finite set of vertices. For a lot of our results, that's all you need to know about what a simplex is. It's just a way of talking about finite sets. But it's also convenient to think of these as the convex hull of some number of points in general position. So a zero-dimensional simplex is just a single vertex. A one-dimensional simplex is an edge, is two vertexes and the edge between them. So, you know, the edge between them doesn't show up in the combinatorial description, but we need this for the geometric description. A two-simplex is a solid triangle. And I emphasize it's a solid triangle. It's not the boundary of the triangle. It's the interior points as well. Three-simplex is a solid tetrahedron. And then you can do the same up to arbitrary dimensions. So these are the two. When we say simplex, we'll sometimes distinguish between whether we mean combinatorial or geometric. But often we'll just leave it uninterpreted. And the dimension of a simplex is is the size of the set minus 1. So you think of the dimension as the smallest Euclidean space that holds it. A simplicial complex, combinatorially, is just a set of simplexes that's closed under inclusion. And again, for some results, that's all we'll need to know. Geometrically, I'm not going to give you the actual definition because it's a little tedious, but it basically says is that you take a bunch of simplexes, you put them in Euclidean space, and you glue them together along their faces in a nice way. You know, you can look up the definition if you care about the details. But this is, you know, the picture somehow sort of conveys the basic idea. So again, we're going to go back and forth at will between these two definitions. The basic morphisms here are what we call simplicial maps. So we're given two complexes. And we take what's called a vertex map, which maps vertices of one complex to vertices of another. But we want to guarantee that it sends simplexes to simplexes. So that in this case, the solid triangle gets mapped onto an edge. But the image of every simplex on one side is a simplex on the other side. And this is one of the two basic morphisms that we care about. And geometrically, this induces a piecewise linear map on the complexes. There's something else that's slightly more complicated that we care about called the carrier map. So what we do is we take a simplex, so we take a complex and we pick, for each simplex in there, we map it onto a subcomplex of another complex. So here the yellow simplex on the top maps onto the region over here. And this is something that we'll use a lot for things like problem definitions. And there's a technical requirement which we can justify operationally later on, which says that we want a carrier map to preserve intersections. That is, the image of the intersection is the intersection of the unions. And this will be important. This will actually have a computational interpretation, which I'll tell you later. To model computations, what I'm going to do is I'm going to use a vertex to represent a process state. So I'm going to label each vertex with a process ID. And in this talk, in order to save space, I'm going to use a color. So here, this is the green process. And then I'm also going to label it with a value, which you can think of as the input value to a task, or the output value. So this vertex here could represent the green process starting out a consensus with input 7. It could also represent the green process finishing a consensus with value 7. We'll use the same device, the same gadget to represent both beginning and final states. And in fact, we'll even represent some intermediate states, as I'll discuss later on. So we use a simplex to describe a global state. So this triangle here represents a state where the blue process has input 0, the red process has input 1, and the green process has input 2, and they have these simultaneously. So the fact that they're linked by a simplex means that they're in some sense compatible with each other. They can all happen at the same time. So what I'm saying here is that this is a global state where these three processes have these three values. And the fact that they're compatible with each other is represented by drawing a simplex between them. So you could imagine, you could say, well, can't you do that with graphs? And the answer is not in a natural way, because if you had a graph, for example, all that would say is that these two states are compatible, that they're pairwise compatible, but it doesn't really say that they're three-way compatible. And so, you can add more machinery to represent this in graphs, but it will become cumbersome pretty quickly. But using a simplex as a higher dimensional generalization of a graph gives us a very compact way of saying that these vertices are, these states, these local states are all compatible with each other. Now, one thing that this representation gives you is a way of graphically telling when two global states are similar to each other. So here we have two global states that differ only in the state of the green process. So in both states, the red process has 1, and in both states, the blue process has 0. But in this state, the green process has 3, and this one has 2. The fact that these two states are similar is represented by the fact they share an edge. These two processes can't tell, based on their local knowledge, which of the global states holds. The green process can tell the difference. By the way, if anybody wants to ask any questions, if I'm going too fast, don't hesitate to speak up. So we can represent a collection of global states as a simplicial complex, and the dimensions of the intersections tell you how similar the states are. For example, if the two states are totally distinct, then their intersection is empty. So that's pretty distinct. So remember that consensus problem that we talked about earlier. Let's consider a sort of special case where the processes just decide on binary values, 0 and 1. So we have three processes, green, red, and blue. And each one starts out with a value 0 or 1. And we want them to agree on one of those values. So this vertex here represents the state where green has value 0, here red has value 0, here blue has value 1, and so on. And if you look at all of the possible ways of assigning 0 and 1 to three processes, you get this octahedron here. So this, remember what I said about using a static mathematical object to talk about all kinds of possibilities simultaneously? Well, this is a compact way of saying these are all the possible initial states of the protocol. Every triangle here represents a possible initial global state. Every vertex represents a possible initial local state. So all possible initial states, the processes are represented in colors, and we independently assign them a 0 or 1. What the output complex tells us what the final states of the system look like. So here, we know that everybody has to either agree on 0 or they have to agree on 1. So there's only two possible final states which are represented by the two triangles. The top one, everyone agrees on 0, and the bottom one, everyone agrees on 1. So here, the output complex is just two disconnected triangles. So we started out with an octahedron representing our global states, and we ended up with two disconnected triangles representing our final states. So the carrier map tells you, if I start out in this state, where is it legal to end up? So if I start out with all 0 inputs, then since everybody has to decide somebody's input and all the inputs are 0, then it turns out that you have to end up over here. So if you start out on this particular triangle, you have to end up on the top triangle. If you start out on the all 1 input, which is obscured by the 3D picture here, then of course you have to end up on the bottom triangle. Because all the inputs are 1, that's the only possible value you can decide. Now, suppose we start out with mixed 0, 1 inputs. Where is it okay to end up? On either one, exactly. So this is why it's a carrier map and not a regular map, because it says that if we start out here, there are 2 possible places you can end up. So that's a kind of an example. So more generally, if I give you a task specification, I'm going to give you a triple consisting of the input complex. This says these are what all of the possible initial states of the world will look like, expressed as a simplicial complex. These are what all the final states of the world look like, expressed as an output complex. And then I'm going to give you a carrier map that says if you start out here, you can end up anywhere over here. If you start out there, you can end up anywhere over there, and so on. So it's just a very simple language for talking about these finite computational problems where you have a finite set of possible initial states and a finite set of possible final states. So that's what it takes to specify a problem. What does it mean to solve a problem? Is it? Okay, so why don't we do what? Yeah. This is a transition. So yeah. So why don't we take a 5-minute break, and then for everyone who can stand it, we'll start again in 5 minutes.